Hello, I'm Diptanshu Mittal. Today I will be presenting my project using the poster titled Advances in Federated Learning via PyFL. Dr. Bapi Chatterjee is guiding this project. Let us start by understanding what federated learning actually is. In many application scenarios like Google's Gboard or healthcare industry, many scattered end users have private dataset. We can collaboratively train a deep learning model by leveraging this decentralized dataset. However, data sharing sometimes is not possible among the end users due to privacy concerns or standard regulations, or sometimes the data volume itself. Thus, instead of data, model updates are shared by the end users. This type of machine learning setting is now popularly known as federated learning. In our work, we provide a custom-built framework for federated learning named PyFL, which can be accessed using this QR code. Our experiment results indicate that the PyFL offers seamless scalability from a standalone workstation to a cluster of nodes packing multiple GPUs. We aim to employ the developed PyFL framework for implementing the following new federated machine learning use cases. Firstly, test out the Frank-Wolf algorithm in federated settings and compare its performance with other standard optimizers like SGD. Secondly, test the neural architecture search algorithm in federated settings using various datasets like MNIST, CIFAR10, and ImageNet. Lastly, test out various aggregating algorithms like Fed-average, Fed-prox, Fed-mid, Fed-dual-average, and benchmark them on parameters like computation cost, conversion speed, model accuracy, etc. So now that we are clear with the project goals, let us understand what aggregating algorithms are and how the federated training actually works. The aggregating algorithm is the algorithm used by the central server to aggregate all the model updates received from the end users and use it to update the global model. Federated training works in the following manner. Here is the pseudo code for the Fed average aggregating algorithm, both for the central server and the referred to as reducer, and the end user referred to as clients. The federated training is divided into multiple rounds. In each round, the reducer samples subset of clients from the pool of available clients. The global model is then advertised to all the sampled clients. Clients then update the global model locally and start the training. Each client locally updates the global model for key epochs using their private dataset. Once the training ends, clients send the global model back to the reducer. After that, the reducer aggregates all the updates from the clients and calculates the gradient, using which the global model is updated. Now let us understand the PyFL framework. PyFL framework embraces all the concepts of federated learning. It consists of central server called reducer, to which end users referred to as clients are connected to. Reducer acts as a central orchestration server which aggregates the client's model updates using the specified aggregating algorithm and synchronizes the global model with the clients. The clients are the simulated form of real case end devices containing private dataset. Both of these entities are connected to the menu storage. We use the following tools in our PyFL framework. Firstly, we use the Minio cloud storage solution for storing the global model after each round and model updates from the clients. Secondly, we used Flask API endpoints required by the reducer and clients to communicate with each other. We also used TensorBoard for visualizing the inference results for each round. Lastly, we used Docker to simulate real case constraints faced by the end users like memory and computation constraints. We carried out several simulations using the PyFL framework. Following was the setup of these simulations. Just to point out, in federated setting, the training was done using 12 clients, wherein each client had a randomly sampled 1000 training data points from the CIFAR-10 dataset. Also, the Frank-Wolf optimizer's constraint was that the L2 distance of the model weights was less than 30 from the origin. And the aggregation method used was that the reducer performed the global aggregation updates after every epoch by the client. We received the following results from the experiments. In the non-federated setting, the SGD optimizer gave 0.928% accuracy, while the Frankfurt optimizer gave 0.9197% accuracy. The SGD optimizer gave 0.9103% accuracy in the federated setting, while the Frank-Wolf gave 0.9007% accuracy in the same settings. The average round time observed in federated SGD was 20 seconds, which dropped to 17 seconds if the optimizer was changed to Frank-Wolf. We refer to the following sources for our project. In conclusion, our experience of working with the PyFL framework has amply indicated that the proposed framework scales on distributed settings, from workstations to multi-node clusters. Furthermore, the experiments exhibit that the federated Frankfurt method converges analogous to federated SGD. Comprehensively, our work presents an excellent platform for applications requiring constrained machine learning methods in a federated setting. That is all from my side. Thank you.